last to last class, we talked about linked list. Linked list is a data structure which is a linear data structure which consists of nodes, and each nodes consist of a data and a address which points to what next node. So this is about linear data structure. It takes about constant time to insert a node in a linked list because we already have the address. We know we have to insert and all. But to search an element in a linked list, it takes a big O of n time. Okay. Then we talked about doubly linked list. Doubly linked list is a data structure which also has nodes, but here we have a data and we have what two address spaces where the next pointer points to what next node and the previous pointer points to previous node. So we can traverse from both the sides, whereas in singly linked list we cannot traverse from backwards. We only have to traverse from one side. Okay. Then we talked about doubly linked list, and then we talked about stack. Now stack is a data structure which follows first in, first in, first out principle, FIFO, or last in, last out principle. Getting my point? So stack is a data structure which follows the principle of first in, first out. That is, I had told you guys to imagine this as an ice cream bowl, and there are different types of flavors. The last ice cream, oh, the last in, first out principle. The last ice cream, the last flavor which you add will be the first one which you taste, or the first one which you add will be the last one which you will taste. So this is about stack, and then we talked about queue. Okay, in stack, what we do, we push the elements at the last position and we pop the element from the last position. Okay, now then we talked about queues. In queues, what happened? Queue is a data structure which follows what? First in, first out principle. That is, the first element to go in will be the first element to come out. Okay, we insert or we enqueue elements from the rear end and we dequeue it or we pop it from the front end. So this was about queues, but we were facing some problems in queues. That is, when we dequeued some elements from here, our spaces would be what? Empty, and our size would decrease. But these spaces will be of waste because when we call the enqueue again, it would say the queue is full. So these spaces were empty. So what we did is we implemented a circular queue to overcome this problem. In circular queue, we keep on moving our pointers, that is our front and rear, in a circular manner so that we manage our space more efficiently. Understand? So that was quick recap about data structures until now. And yesterday we talked about hashing. Now, hashing is a data structure which stores a key value pairs. That is, there are some keys. When we pass it to a hash function, we get a hash, or we call it as an index. If you're using an array, you call it as index. We get a hash. That hash value, that is like 0, 1, 2, 3, we insert it in an let's say array or any. You could use different types of data structures or you could create your own, but usually we use array over here. So this is what a hashing technique. So in hashing technique, we faced a problem. The problem we faced is when we hashed, when we hashed, we got what? We got same keys. That is, the keys were different, but the hash value was same. Let's say for key 1, I got some hash value 0, and then I inserted 11 over there. For key 2, I got some hash value 2 and I inserted 18 over there. For key 3, I got some hash value 3 and I inserted 15 over there. But for key 4, I got the same value, that is 3. So what I did, I took the help of linked list and I linked this 15 to what? I linked this 19 to 15. That is, I pointed 19 from 15. Getting my point? What is happening over here? I took the help of linked list. This is known as what? Closed addressing, or we could also known as no. We could also call this as open hashing. So here, what happened? We had a collision. So we had to take help of separate chaining. We are chaining it, but it is not in one go. It is what separately chaining it. The same way, if you have 5 to 6 keys, and let's say collision happens, then we can do chaining. That is separate chaining. That is, we resolved our collision. The collision which we had was resolved by this method called separate chaining. That is what we learned in our previous class. Now let's move to open addressing. The separate chaining and open addressing are two different methods of collision resolving techniques. So what is open addressing in hashing is, it's a collision resolution technique in hashing where all elements are stored directly within the hash table. So what does this statement wants to say? So this is what separate chaining. In this, the elements are outside the hash table also. Are you guys following up?
Hmm.
In this, what happens is
Yes.
the elements which are there, they are not present in hash table. They are present outside the hash table. And that's why we call this as open hashing or closed addressing. Open hashing or closed addressing. Remember these terms very carefully. They are a bit confusing. This is open hashing or closed addressing. Okay. So elements are not present directly inside a hash table and they are present outside hash tables. Okay. Now let's move on to our next collision resolving principle, that is after separate chaining. Now we are talking about what? Open addressing. Okay. Or we could say is this as closed hashing. Open addressing or closed hashing. Let's say you have a key and a value pairs. So when I insert this key1 into hash function, I get some hash value 0. I insert my element. Let's say I have some elements 11, 12, 13, 14, doesn't matter. I insert 11 in position 0. Then I have key 2 which I pass from hash function and I get a hash, that is, I call it as hash value, or you can call it also as an index because we are using an array, and that I insert it in at position 2. Then I get key 3, I take key 3, I get some value 3 and I insert over here. Now let's say for key 4 I get the same value 3. So here what happened is I had a collision. That is, for key 4, the hash value, when I passed it through hash function, I got a hash value of 3. The key 3 also showed me value of 3, but key 4 also showed me value of 3. So what do I do now? I'll just simply search an empty space after the position 3. That is, from position 3, I will traverse it. If I find an empty space, then I will insert my element over there. Let's say my fourth position was empty. So what I did is my key four's value, I placed it over here. Are you guys following up what's happening here?
Yes.
So what I did is I searched for an empty space over here and then I simply inserted my element over here. That's it. So this is what this is closed addressing, or this is not closed addressing, this is closed hashing, because here elements are not leaving our hash table. Getting my point? So a simple definition for this, this technique is known as open addressing, and it is a linear probing technique. That is, we linearly search for an empty space in a hash table, and if we find one, we insert it. Okay, now let's say I have what I have a key. Uh, let's say I have some more keys, and this zeroth position, one position until fourth position, every index is filled with some element. Let's say this first position is also filled with some element. Okay, imagine here there is an element and there are lots of keys, and I have some new key. The new key is pointing to what? 11 now. The new key is what? Giving a hash value of index 0. But my index 0 has already an element inside it. So what I do is I traverse it. I keep on traversing. I'll go to the first position. I see, oh, there is an element. I go to the second position. I see there is an element. I go to third position. I see there is an element. Fourth position, there is an element. Fifth position, that is empty. I'll place it over here. So my key X, when I passed it through hash function, I got an index of 0. But from 0 until 4, I had all my elements filled inside the positions. So what I did is I placed that value inside index 5. Okay, understand what is happening?
Okay.
Now what I'll do is,
Okay.
let's say I want to delete an element present at position 1. So what I did is I searched for element in position number 1 and I deleted it. Okay, so now this first position is what? Empty. Okay, this position is empty. Now I had to search for my element which was inserted at position number 5. That is with the index 0 only, but we had used linear probing, so it came to what? It came to position number 5. So my key X, when I put my key X, I go to hash function and I get a value of index of 0. So one method for this searching in this linear probing is that if you don't get the element at the desired index, what you do is you traverse it until you find the element or until you find an empty space. Are you guys following?
Yes.
Hmm. So what happens is when I try to search an element in linear probing, if I don't find the element at that index, what I do is I simply traverse it. I simply traverse it I found I I until I find the element which I'm looking for, or until I find an empty space. Because what empty space indicates that my element is no longer available. That is, if we had an empty space, then definitely we would have stored element over there. So what I do is when I search my element X, that is from key value X, I pass it through hash function, I get a hash value of 0, and then what I do is I traverse it. I traverse it. We are looking for element number 19. Element 19 which is present at position number 4. But here there is an empty space. So if I don't find my element 19 over here, I simply traverse it to position number 1 and we found an empty space. So we return what? The element is not found. But in reality what? My element is present and it is present at position 4. So what happened over here? We are facing a new problem. That is when we want to search an element, but there is an element already deleted between these in between the original index of this element and the present index of this element. There is an element already deleted. So what do we do here? We put a deleted marker. That is, we add a tombstone. That is what we simply put X mark over here. That is what it indicates. There was previously an element present over here, but now it's not. Getting my point? What is happening over here?
Yes.
So now when I search for this element 19, I pass my key 8, I go to hash function, I get a value 0, and I see the element. No, it's not the element which I'm looking for. I traverse it. Here there was an empty space, there was an element which we deleted, so there occurred an empty space, but we have placed it with deleted marker. So now I know there was previously an element, so what I do is I traverse it again. I traverse it to 18. This is not the element we are looking for. I traverse it further, I traverse it further, and here we are, our 19 element which we were looking for. I finally found it, and then I return this value. So this is how you search and how you resolve problem in linear probing. Linear probing. It is simply search for the next empty index from the original index if your original index has already filled. Okay, understood the concept.
Okay. Hmm.
So this was about linear probing in hashing. Let's try to understand. So the hash function which we will be using today is the same function, the DJB2's algorithm for strings, in which we pass our string value and we multiply it by 2 power 5. That is, you know this bitwise operator in the last class I taught you, or we understood this bitwise operators. Okay, then I return what? Uh, Hash int modulo the table size. Why we use modulo? Because we don't want our hash value to exceed the table size. Okay, so this is the algorithm which we'll be using. This is the what hash function we will be using in our inserting and deleting on today's linear probing also. Okay, so how do we insert an element in linear probing? It's let's see it. So we take a bool value, and why we take bool value? Because we just want to return whether it's inserted or not. So we just return true if it's inserted and no if it's not inserted. So we call a function insert. That is, we define a function insert linear probe, and then we pass our table, we pass our key. So this is key. There is a small typing mistake, I guess, and we pass a value. So if my table count is greater than my table size into 7. So what are we checking over here? I told you guys about load factor, remember?
Hmm.
So here in separate chaining, we usually do not care much about load factor because the elements are what present outside the hash table also. So even if our table is filled, we technically can store our new elements outside the table. But in linear probing, the case is not mm, like in separate chaining because all the elements are present inside a hash table. So our load factor, that is the number of elements divided by the total size of my table, should be what? Should be always less than 1 or less than 0.74, less than 5 actually, because we need very minimal collisions to happen and we need lot of spaces in between. Okay, so our load factor should be what? Minimum, that is what? At least less than 0.75. So we are checking it over here. We are checking that if our load factor, that is, if our load factor, that its table count is greater than equal to table size into 0.7, ultimately we are checking the load factor and we are printing. If the load factor is too high, then we print it's too high from 0.7, and then we return false. That is, our this function ends over here and we return false. That is, insertion was failed. And if this condition is not satisfied, that is, we have a lot of space and our load factor is less than 0.7, we move on ahead to we declare an index which is unsigned long. Again, unsigned is stands for what? A positive
Positive
registers.
numbers.
A positive what? Data types. Okay, and we here call our hash function. The hash function we are using is that DJB2's algorithm. As I say, we pass key and we pass table size, and in return we get what? Hash modulo table size. That is, we inserted an index. So now our index holds some value between, uh, let's say our table size is 10, then our index holds a value between 0 and 9. Okay, now I declared again an original size, original index. So our original index is our index because we don't know whether we have to insert in our original index or we have to linearly probe until we find an empty space. So my initially my probe count is what? 0. Usually when we probe, that is when we traverse it, we call it as we are probing it. Getting? Now I'll run a while loop. I'll run a while loop. If my table entries is not equals to null and my table entries index is not equal to deleted marker, then I'll run it. Okay, so what does this while statement says? See, my table entries index, that is what? If my elements are not equals to null, that is what? If the elements are full and if there it's not equals to deleted marker. So here there is one more possibility. Let's talk about that possibility. Now when I deleted this first, that is the element in the first position, now I want to insert an element. So what I do is I previously had a deleted marker over here. When I search for an element 19, then I know that there is a deleted element over here and I had marked a deleted marker over here. So I'll move forward. I'll keep on probing until I find my element. But while inserting a new key, that while inserting a new value, let's say key n, then I know that there is a deleted what element over here and that I have marked it by my marker and I say this is a deleted marker. So what I do is I remove this tombstone, that is I remove this deleted marker and I insert my value in this. So now you know why this loop is important. See, if my table entries is not equals to deleted marker, that is, if this condition becomes false, we exit this while loop. That is, we exit the probing. That is, we exit the what? The linear probing that we were doing earlier. Okay. So here what we are checking. Now this strcmp, that is string cmp. What does this do is it compares the values. That is what values? It compares the characters, the string characters. And if the string characters equals to 0, then we simply add the value over there. Okay. And then we print, we inserted it and we return true. Okay. And if this condition failed, what we do? We go to our index, we add one and we modulo it by table size and we say probe count plus plus. Okay. This is simply what we are searching the next index. But to make things a little good, that is to avoid collisions, what we do it modulo by table size. Okay. That is what linear probing, that is we move to the next slot. And if the table is full, if the index equals to original size and our hash table is full, we return false. That is, we did not insert anything. Okay. And now after all this, our while loop is terminated. Now if this condition did not, so where actually is our main code is over here. That is what? If we compare the index to our keys and we compare it to keys, that is our index keys to keys, and if this equals to 0, that is this standard strcmp, this function, it compares all the string values and if they are same, it returns what? It returns 0 if they are same. Okay. And when it returns 0, we go to table size, we go to value and we insert the value in that index. And when we inserted value in that index, then what we do, we print it, that we simply inserted the value in the index and then we return true. That is, our insertion was successful. Okay. And then we directly break from this loop. That is what we return true. Directly we are breaking, ultimately we are breaking directly from this function by returning a value. So all these codes will not execute. But let's say we did not insert anything, and let's say we already probed it, and we did not find an empty space, and our table was full. This usually do not happen because we already have an if condition over here. That is, if our table is filled more than 0.7, that is more than 70%, then we'll simply exit. But let's say I forgot to mention this, and then I came over here, and this code helps me that my hash table is full and I return false. Okay, now I terminated from this while loop and I came over here and I create a new entry and I pass what? False. Okay, and then what I do is if if I found an empty or a deleted slot, that is what? If I found like in over here, what happened is this element, this index had what? No elements. That is, there was an empty space over here. So if I found an space like this, what I would do? I would go over here. I would go there. I would create a new entry. And then if that new entry is not equals to null, then I would return false. But if it is equals to null, then I would go inside and I would insert my new entry over there. And I would say my table count is plus plus. So what is happening over here is when you check this, so here we have our linear probing, and this was previously what? Marked. That is what we marked this at index 0 as what? There was a previously an element present. Okay, we marked a tombstone. Now when we want to insert it, what we do is I use the while loop, and the while loop will be true till where? If I found an empty space till here. Okay, let's say my table is what? Full. Okay, let's say my table is full and I have some deleted markers in between. And the first deleted marker after the original index is present at index 1. So when I traverse the while loop, it moves over here, it checks the element is full, it moves over here. Now it checks the elements is full. So I do not use my while loop to insert an element over here. See, in this code, my while loop is not inserting an element in the deleted element, that is in the tombstone. It is not inserting it over here. It is simply returning that this is what? Full. Okay, and then I move over here and here and here and here and I return my table is full. So the problem we are facing over here is there is an empty water. There is an empty space which we have marked as deleted marker and which holds no element. So what we do is we call a new function. We call it and we call it as new entry and we pass key and value. That is, we create entry over there because previously we had assigned an tombstone for there. So what we do is we create a new entry over there and we say if my new entry is not equals to null, then we return false, and if yes, then we return true and we move forward and we insert, that is table entries dot index. So what was the index over here? The index 1, and we return value, the that is what stored in new entry, that is value. We return the value over there and then we simply increase our table count to table plus plus. Okay,
Okay.
now you understood how we insert an element in linear probing. So let's move to how we search an element in linear probing. Let's say I have to search an element in linear probing. So we talked about all the cases. That is, if there is an element missing over here, we add an tombstone over here. And if there is an element which is not present in original index, then we simply traverse it until we find an empty space or our element itself. Okay. Now let's move to how we search an element in a linear probing. we call a bool function, that is we return true if our element is found, and we return false if our element is not found. We go over here, we search for a linear probe, we call this function, we pass a table and we pass a key and we pass a value. So we are assigning again index, that is we are calling the function because uh, the way you inserted this was by passing it through hash function. So now way to find it is passing it again through hash function and getting the original index of it. So when once you find the original index of it, then you store that original index into original index, and then you probe count, that is your probe count is 0. And well type table entries is not equals to null. That is what? Unless my elements are present, what I do is I use the while loop. I keep on traversing it. Okay, if my table entries is not equal to deleted marker. So if my table entries is not equals to deleted marker, if this condition becomes true, then what I do is again inside this is now nested if. Then I compare my key to table entries index dot key. That is I compare my table entries indexes key to my key. And if this is equals to 0, then I point my value, that is value at value equals to my value. Getting my point? So this is value at value, that is we are using this pointer. You call this star symbol as value at. Value at value. We are storing it with value. That is we are not actually what? See what I am doing over here is I am not copying this data, but instead I'm pointing my pointer to it. Once I point my pointer to it, then I could simply return my pointer's address. I could simply return my pointer and it would show the element over here. Okay, so that is why I'm using a pointer over here. And then I print just I found the key at key position, and let's say I had to what? I had to traverse it. Then I will just pass my probe count. So if this condition failed, and if this condition failed, so what I do is I do index plus 1 and modulo table, and then I do probe count plus. Okay. And now if my index is equals to original index and I do break. So what is happening over here? Let's try to implement this code over here. Okay. Let's take it side by side. Let's see whether I'll be able to do it side by side or not. I don't think I'll be able to do it side by side. So you guys have to, okay, like this only we have to search it. So while I'm searching this, now my table entries is not equals to null. Okay, while my table entries is not equal to null. So if my table entries index is not equals to deleted marker. So here my table entry is not equal to deleted marker. Am I right? So here my element is present and this is not equal to deleted marker. Am I right?
Hmm.
So
Yes.
what I do is my if condition becomes true over here. I go inside and I check the key for key, and if it is equals to 0, I go inside and I check the key, that is 0. What key I had passed, and the key for this index 0, that is when I pass it to hash function, are returning the same keys. No, they are not returning the same keys. No. So for element 11, there was key 1. So my key 1 is not equal to my key x. Getting my point? What is happening? I am
Hmm.
searching for what? I am searching for 19. The keys are different. My hash value is same. That does not mean if my hash value is same, that does not mean my keys are same. My keys are different. And that is why we are comparing our keys. Now when I compare these keys, it won't return me 0 because my keys are not the same. So it is not equals to 0. What I do here now, I exit this if statement. That is if statement. This nested if statement will not execute. Now, getting my point, why this nested if statement won't execute? Because my key is not same. My value is different. My index might be same. Not sure in all cases, but my index might be same. But my keys are totally unique. That is why the social media apps ask us for an unique username because those act as keys for us, which saves all our data. In if our index is same, that doesn't mean our key is same. Okay, and then I go back over here, and then what I do is I do index plus one modulo table size. Instead of this, what we'll do is we'll just linear probe it and we move over here. Okay, and then we say our probe count plus plus, and we check whether our index is equal to original index. Why are we doing this? You'll get to know. Let's say to understand this statement, what I do is, let's say my table is full, and what I do is I keep on traversing it, traversing it, traversing it, traversing until I loop it. I come back over here, and I come again to my original index. So what happened is this while loop, if I did not add this statement, this while loop will be executing for infinite time. Getting my point? So when
Okay.
I traversed all my indexes once, and when I reach to the original index again, then what I do is I break this while loop and I return my element. It did not, and I did not found my element. Okay.
Okay.
So we do not want this statement now. That is because we have an empty space over here. So if we found an empty space over here, we return simply our element is not found, but our element is already present over here. So we have to return this 19. Let's see how will we return this 19. So let's move to our code again. Now now again we check whether when once we traverse it, that is our new index is what? Our new index is 1 now, and we traverse it. Now, is this not equal to deleted marker? Now here the first if condition only becomes false because here previously there was an element, but now I have marked this as a deleted marker. Getting my point?
Yes.
So when I mark this as my deleted marker, we know that there is no element present over here. So what I do is I simply traverse it. That is what I'm doing over here. I do not go inside and I do not check it further because I know that that is a deleted marker, and I simply go and I probe it. And then I will traverse it. I traverse it again. I move over here. 18, I move over here. And let's say I move over here finally. So here, let's say our index is 4. Okay, let's check. If my table entries index is not equals to deleted marker, that is what? Element 19 is not equals to deleted marker. Yeah, that is true. And so we move inside our if again, that is we move to nested if and we compare the key values. Now the key which I had given to search, that is we search element not by their data but by their key. The key which I had given for this 19 and the key which is already present while inserting this 19, both are matching. Getting my point now?
Yes.
So these both keys are matching it. When this match, what I do is I go inside my if statement and I point my pointer toward this 19. Okay, and now when I point my pointer to 19, what I do is I simply return that my key is present at, I return my value and I return, I found it, I found the key at position uh, after some probes. Okay, and then I exit this while loop. Okay, so this is what is happening over. here. That is what we were searching our linear search. So this was about linear probe in hashing. Now let's move to what? Quadratic probe. Now this seems little what disturbing, but it's easy, trust me. Okay. Here in linear probing, what we used to do, we would just simply traverse it. Okay. Now here, let's say we have some key value pairs, we have a hash table, keys and hash function. What I do is, uh, I pass my key one, I pass it to hash function, and then I go to, then I get an index one, and I pass my element over here, and then I go to key two, and get a hash function over there, and then I pass it to index zero, and I insert it. Now what happened is, when I pass this key three to my hash function, what I got is index 1. But to my surprise, index 1 already had an element present inside it. So what I do now is I square the index and I add 1. That is what? I square the index. What is my square of the index? 1. That is 1 square is 1. And I simply add it to 1 and that becomes what? 2. Now I move to index 2 and I store my value for the key 3 inside index 2. Did you guys follow up what happened over here?
Yes.
So here for key 3 which pointed to my address number 1, but my address 1 was filled. So what I did is I squared the index and I added 1 and I inserted my element towards that index. Now when I pass key 4, this pointed to 2. So this was a new problem because the original element which had to be stored in 2 was already stored with the index 1, but that is already stored. That is in simple words that the index was filled. So what I do is I take the index, I square it. Once I square it, it becomes 4 and I add it. Now we get index number 5. So the key number 4, that is the value of key number 4, I simply store it at position 5. Getting my point what is happening?
Yes.
Let's say to our worst condition, my key 5 points to position number 5. And this is also filled with some element. Now what I do here is I take my index, I square it, becomes 25 and I add it once and it becomes 26. And then I store my value over there. Okay.
Okay.
So in quadratic probing, if you find an element fill, what you do is you take the index, you square it, and then you insert it. Okay, so this was a simple explanation of how quadratic probing works. Well, when we see our code, you might find that instead of this indexes, we are taking the hash function itself, and we are instead of this squaring index, we are squaring our hash function itself. Okay, let's try to insert an element in quadratic probing. So what I do over here is I I take my return type as bool and I insert my table, my key by value to this hash to this insert quadratic probing, and then I check. Now I check for my load factor less than equals to 0.5. That is, if my load factor, that is, if my hash table is 50% full also, what we might encounter some serious issues. That is, let's say this is of size 5, and let's say I go to element number 4. So what is 4 square? That is 16 plus 1. 17. So the 17th index do not is not present on in our hash table. So it may lead to some problems. So what we keep our hash table very large. That is, if our hash table is even filled for 50%, we simply return that quadratic probing is not possible over here. That is, it is possible also, but still we do not want collisions in our what in our implementation. That's why we return it's better warning load factor. We return war and we just exit our function. And then as always we assign our index to hash function. We call the hash function and we assign our index and we assign our original index and in int I equals 0. Okay, so while I is less than equals table size, what I do is probe index equals original index multiplied by I modulo table. So what I'm doing over here is I am just squaring it and I am what? I am modulo ing divided by table. That is like the problem we faced over here, 14 square 16 plus 1 17. So this problem should not happen. So what we do is 17 modulo my table size, and now what that gives an index which is present inside our range. Okay, are you guys clear on this?
Yeah.
Yes.
Now if my table size that is if my table entries and my probe index are equals to null and my table index probe index are equals to deleted marker, let's say I have an empty space over here, and when I did what index square plus 1 and I found out that this fifth position is empty, let's say this is empty, then my if condition will become true. And when my if condition becomes true, what I do is simply I create a new entry, I store my values in my new entry, and then if my new entry is filled, I return false, and if my new entry is empty, then I keep going forward, and what I store my value in my probe index as new entry. And then I count my table, that is I increase the count of my table to count plus plus. See, my table count is how many elements are present inside my table, whereas my table size is what is the actual size of my hash table. So we do not need to we do not need to increase or decrease my size of the hash table. Instead, we have to increment or decrement our table count. Okay, so the table count and the table size are totally different terms. Don't get confused. Okay, and then once this is done,
Okay.
we just simply return that we inserted our value of key at probe index and 1. Okay, and then I return true because we are using a bold return type. Once I return true, then this whole function will be exited. Okay, now what? Let's say my uh, table dot index probe index and key both are same. If both the keys are same, that is the key which I gave and the key which is already present, that is, let's say I passed an element that is 19 and now I'm passing a new element that is 31. Okay, if the keys are same, this usually do not happen, but if the keys are same, this condition becomes true. And once this condition becomes true, we say our value, we insert our value at that position and we simply return. Okay, so what is exactly happening over here is, let's say I want to insert an element at some position, and then I found out that and then I found out that when I uh, did once when I probe it once, I got to this index 2, and let's say there was previously an element present over here, then the key value of this previous element is what? Some key value, that is, let's say key value 3, And now I'm inserting key value 3 over here. So my element is already present in my hash table. Getting my point? So the element which we wanted to insert is 19. But I found that my element 19 is already present in my hash table. We do not need to insert 19 again. We just return our what probe index. Getting my point? What is happening over here exactly? You guys following up?
Yes.
So what happened is I had to insert an element 19, but to my surprise I found that my 19 element is already present over here. So what I do is I simply return the index of it and I say that it is inserted. Let's say you had logged in to a social media account a while ago, that is a very long ago, and today you are back and you are trying to sign up. Instead of signing in, you are trying to signing up. So what happens is now your data is already present in the database. So what did it do? Now while signing up also you may see it returns that the your data is already present, or it just simply signs you up and you get inside, but all your data is still visible to you. So that is what happening over here. You guys getting my point? So this is how you insert an element inside quadratic using quadratic probe. Okay. To wind
Okay.
things up, I'll just simply say if my key 3 has already pointing to an index which is already filled, what I do is I take the index, I square it, or simply I take the hash itself, I square it, and then I added 1, and then I inserted my element to my new hash. Okay, instead of calling these indexes, I call this as hash for our better understanding. Now, because we are using an array over here, it is wise of me to use this as indexes. But if you are not using an array, it is a good practice to call these indexes as a hash. That is, if we pass a key 3 and we get a hash function and we get a hash, we got a hash at position 1, hash of 1, that is what hash of 1 is position of 1. And if the element is filled over there, what I do is I square the hash, that is I square the index, both are the same. I square the hash, I add 1, and I go to my new hash, or I could say I go to my new index and I check whether it is empty or not, and if it is empty then I simply add my element over there, and if it is not, I take the index or I take the hash, I square it, I add it, and then I go and then I keep doing unless I find an empty space and I add my element, that is I insert my element in that empty space. Okay,
Okay.
so this was
Okay.
about quadratic probing. Now the
Hmm.
problem here is how do we search quadratic probing? Because this is so complicated, what I do is I implement some techniques. I call my search quadratic probing function over here. I pass my table, I pass my key, I pass my value. Okay, then I the value will be passed automatically when once I pass my key. Okay, so I go to I assign my original side or original index star slash I modulo table size to my original index, and then I go to while loop. While I is less than table size, my I is what 0. What does this I say? I says the what the probing. It's simply probing. Okay, and then while my I is less than table size, I go inside probe index, and my probe index is original index plus I, that is the same as original index, but my original index was updated to this, so my probe index will be updated again. So my original index and my probe index are not same anymore. although my mathematical functions and the names are same, but the value of this original index, my probe index, are totally different. Okay. Now, if my table entries, that is probe index, equals to null, then I return false. That is what, let's say, I have to find this element 19, or let's say I have to find this element 31. What I do is I pass my key, I go to position number 1 because it is pointing to position number 1. I go to position number 1, I square it, I add it, I go to position number 2. There is already an element present over here. So what I do for searching, I square this number and I go over here, and I found that my element is not present over here. That is this index is completely empty. Then simply I break the loop and I return that I did not find it. Getting my point? What is happening in its first three lines?
Mm-hmm.
Now,
Yes.
if my table entries is not equals to deleted marker, let's say I deleted an element over here before searching my element 45. Okay, I have to search for this element 45, or let's take this example only. I had to search for this element 33, and I deleted this 19 element. That is, I deleted element in position number 2. Now what happened is this created an void for me. That is what? This is now an empty space. So to counter my problem, what I did is I inserted my tombstone. That is what? I inserted my deleted marker over here, so that I know that previously there was an element present over here, and once I inserted my deleted marker, I know that there are still elements present further, and then I could just use my probing techniques and find the element. Okay, so what I do is not equals to deleted marker. Now uh, here I check whether my 31 is not equals to deleted marker. So yes, 31 is not equals to deleted marker and is an actual element. Getting my point? So my if condition becomes true over here because 31 is not a deleted marker and an actual element. Now I compare my keys. That is, the key present for 31 and the key which I passed are both the same. And once I found out both the keys are same, then what, my second condition becomes true. And then I go and then I simply print the value and then I return true, and then I break this searching technique, this searching function. Okay, you guys got my point, I guess.
Mm.
So to simply wind things up, I'll what I'll do is um, from here, yeah, hashing is a technique in which you uh, pass your what values, key value pairs. Hashing is a data structure which holds key and value pairs, that is pairs. Usually we are using arrays over here, that is why I'm not calling this as key value pairs. Instead, I'm calling this as indexes and values present inside the index, but usually we call this as key and value pairs. So hashing is a data structure which holds key value pairs, which previously which was passed by hash function. Okay, so here we have some keys, we pass it through hash function, we get some hash values that are indexes for our case, hash function in which we store our desired value, or we could store our actual key itself, doesn't matter. Okay, so we encountered some problem in this hashing. That is, let's say my key 4 points to the same hash. My If my hash is same, that does not mean my keys are same. My keys are always new and always unique. Okay, keep this one thing in mind, that is, keys are never the same. Keys are
Mm.
always unique, but a hash might be same. Okay, okay,
Okay.
guys. So we encountered a problem, that is, we encountered a problem encountered a problem, that is what, uh, my key 4 was pointing towards
Collision.
key 4 was pointing towards 0. So to resolve this collision,
What we did is we took the help of there are multiple resolution techniques, that is separate chaining and open addressing. Now we took the help of separate chaining. Where did that separate chaining go? Yeah, separate chaining. And what we did is we simply pointed my new element to that index itself. So here my hash value did not change. Instead, we pointed it and we will traverse it to find it. So this is separate chaining. Here, the elements are even present outside the table. Okay, so this was about separate chaining, and there was one more method we used, that is open addressing. In open addressing, what happened is we did not leave our hash table. That is, we were always present inside our hash table. Uh, where is that? Yeah, here. We did not leave our hash table. That is, if we found a key, if we found a hash which is which has already present an element inside it, we simply probe it. Here we are using linear probe, we are using quadratic probe, and there is a technique, double hashing, which we will see in tomorrow's meet. Okay, so in linear probing, what we do, we took the index and we just simply added one, that is we linearly are probing it unless we find an empty space and we insert an element. So this is what happened in linear probing. And to make things more complicated for hackers, what we did, we used quadratic probing. Okay, in quadratic probing, what happened is I took all the indexes, I mean all the hash values, I squared it, I added to 1 if my element was filled, and then I moved to the next elements. And this way we inserted elements in quadratic probing. Okay, so let's understand what are the differences in this linear probing and quadratic probing. So separate chaining and open addressing. The definition is uses linked list. For most of the cases, it uses linked list or other structures. Okay, to store multiple elements that hash to the same index. That is what my hash did not change. That is, my index did not change. I was simply pointing my elements inside that index only. Getting my point? What is happening in separate chaining?
Yes.
Now, the open addressing definition is what stores all elements directly within the hash table. That is, we never left our hash table. Unlike this separate chaining, all the elements are present inside my hash table. They do not leave my hash table. Okay. Now I move to
Okay.
structures. The structure of separate chaining is usually array index pointers to linked list or chain of key value pairs. Here also, the array itself holds all the key value pairs, no external structures. That is, we do not need a linked list or we do not need a pointer to point our element. Okay, so collision handling. Collision elements are stored in the same bucket. Now, what are buckets is these empty spaces, that is this index 0, this we call it as bucket number 0, bucket number 1, bucket number 2. Now because we were using arrays over here, so we would call this as index 0 and the array index, so that is what we were calling, but usually we call this as buckets. This is bucket number 0, bucket number 1, bucket number 2. So that is what buckets are. Don't get confused over there. Okay, uh, are stored in the same bucket. Here, what collision elements are stored in different slots based on probe sequence. So see here, it doesn't matter if you call it bucket, or you call it slots, or you call it anything different. It should just what give out your ideas. Okay. Now collision elements are stored in different slots, that is different buckets on probe sequence. That is, if we use linear quadratic or double hashing. Okay, now this double hashing is some technique which we will be studying tomorrow, and this double hashing is very naughty. Okay, let's try to understand it tomorrow. Let's take a whole class to understand this double hashing. Okay, now spatial utilization requires extra space. But here, since all my elements are present inside my hash table only, we do not require extra space over here. Okay, but there is a performance drop is. Why the performance drop is, um, we have to keep on traversing it. Let's say to our worst case scenario, what happens in our worst case is we have to go n times, that is big O of n times linearly. Or if we are using a quadratic, then we have to go quadratic times to find the element. Okay. Now the load factors. The load factor can exceed 1. Why it can exceed 1? Because the elements are not directly stored inside the hash table, they are stored outside the hash table also. So the load factor can exceed 1. Okay, but here the load factor must must be less than 1 to prevent long paired sequences or failure to insert. Okay, then our insertion time. So our insertion time is very short, but let's say there are a lot of elements in our chained bucket. In our chained bucket, there are lots of elements, so it will take big O of n to insert the elements. Okay, in our open addressing, big O of 1 average, okay, to find what to insert an element. Let's say to our worst case, that like this case which happened over here. Let's say I wanted to insert 45 and the index, that is the key, when I passed it, it gave 1. So what I had to do, I had to keep on probing it unless I find an empty space. Let's say to our worst case, what I did is I kept on probing it, and I found a last bucket which was empty. So that became big O of n for me. So that was big O of linear time complexity in worst case due to probe sequence. Okay. Then the search time. It takes 1 plus, what is this? This is our load factor. Okay. Depends on average chain length. Here approximately constant time for because load factor is 1. Now search time depends on what? Load factor. Okay, keeps this in mind. Search time depends on load factor. So deletion is easy, but here deletion is complex because we have to check for elements, we have to mark it as a deleted marker, and then we have to check each. So we were using while loop, we were using in if statement, we were using nested if statement, and then we were calling for pointers. So there was a lot of things happening in open addressing, so the deletion is a bit complex. Okay. Now, primary clustering problem. Now, what is clustering is, let's say, uh, here what happened is, in my linear probing. So here there was an element present over here. Let's assume there is an element present over here, and let's say these indexes are up till what 100. Let's say 1,000. 1,000 indexes are present, and then my new key value, when I passed it through hash function, and then I got a hash of 0. So what I did is I got over here, I probed it, this was filled, I probed it, this was filled, I probed it, unless how many times I probed it? I probed it 999 times. So what occurred over here? This is a cluster. So all these elements which are filled in this hash table are now called as cluster. Okay, now you got what, now you understood what are clusters. Clusters are, huh, clusters are what? Um, a type in which there are no empty spaces in between your original index and your what empty space. That is, there are lot of elements present in between them, which lead to a new problem. Getting my point? So, in
Yes.
open chaining, clusters are not that important because we are using linked list. But in linear probing, cluster might do us some serious damages. Getting my point? So, memory cluster problem is absent, but here memory cluster problem is present, especially in linear probing, because Once you start linear probing, and let's say you have no empty space unless certain big amount of number, that is unless 1,000 indexes, you do not have an empty space. Now what is that? It leads to a serious cluster problem. Getting my point? Now here memory overhead, that is what, lean higher. Why it is memory overhead is higher? That what is memory overhead actually? What is memory overhead? The extra memory used by the system for its own internal operations. That is known as memory overhead. So here, uh, now we defined our hash table, but to our surprise, we are using linked list also. Once we start using linked lists, we know that we have to allocate some memory for the elements to use linked list. You guys following up?
Yes.
Huh. So memory overhead occurs, and it occurs highly because of linked list. But in open addressing, memory overhead does not occurs because all our elements are present inside my linear inside my open addressing, that is inside my hash table itself. Okay. Now preferred, when do we prefer separate chaining and when do we prefer open addressing? We might prefer open addressing, or we might prefer separate chaining when frequent insertion and deletions, upgradable loads, or large data sets. We might need what chain separate chaining. But when we have low memory, that is when we are running out of memory or when we have to utilize our memory to their max, then we use what? We use we use open addressing. Okay. So here I want to make things clear that open addressing is also known as closed hashing. You just need to remember this once. Open addressing is known as closed hashing, whereas open hashing is known as closed addressing. Totally opposite. Open addressing is also known as closed hashing. Why it is closed hashing is because all the elements are present inside my hash table itself. Okay, keep this one statement in mind. This statement might confuse you for decades. Open addressing is what equal to closed hashing. Or you could just remember this as open addressing is also known as one dimensional array. Okay, and my all elements are present inside this one dimensional array or open addressing. Getting my point? So with this, let's wind up today. I thought today's class was fascinating to learn some new things
Mm.
about this data structures. You see how useful and how complex things are becoming now.
Yeah. Mm.
As time now, tomorrow I'll try to finish off this double hashing. Double hashing is also very next level.
Mm.
Instead of using hash function, we use two hash functions over there. So by using one hash function only, we are facing so many difficulties. Now just imagine if we use two hash function. So that is known as double hashing. The name itself says we are using two hash function. Double hashing. Okay, let's understand it tomorrow. So this was it for today. Then let's